The most ambitious structure humans have ever proposed for low Earth orbit would be built from the one material that the LEO environment is most chemically optimized to destroy. And the orbital altitude that makes it work is the same altitude where that destruction runs fastest. That is not a design flaw you can fix. It is not an oversight in the engineering drawings. It is a property of the atmosphere at the altitude where the structure has to exist, and it has been operating continuously on every surface humans have put there since the first satellite crossed 200 kilometers. The diagrams are the problem. Every illustration of low Earth orbit shows a clean arc above the planet. Satellites and stations floating in vacuum, separated from the atmosphere by the thin blue line of the horizon. The vacuum part is true. What the diagram does not show is what is moving through that vacuum at the altitude where large structures are practical. Between roughly 200 and 700 kilometers above Earth's surface, the upper edge of the atmosphere is full of oxygen atoms. Not oxygen molecules, not the paired atoms you breathe, but individual atoms, each one stripped apart by solar ultraviolet radiation coming in from above. They do not glow. They do not show up on the diagram. They are simply present in enormous numbers, moving at the same orbital velocity as any structure that passes through them. When a satellite or station travels at 8 kilometers per second relative to those atoms, the atoms are not drifting gently against the surface. From the perspective of the structure, each atom arrives at impact velocity. 8 kilometers per second is roughly 23 times the speed of sound. A bullet from a high-powered rifle travels at around 1 kilometer per second. The atoms hitting an LEO structure arrive at 8 times that speed, individually, and there are approximately 1 trillion of them landing on every square centimeter of exposed surface every second. You cannot see this. There is no sound. There is no heat bloom. There is just chemistry running without interruption every orbit for as long as the structure exists. The chemistry is direct. Each oxygen atom hits a surface molecule with enough energy to rip the chemical bonds holding that molecule together. It oxidizes what it hits, meaning it chemically combines with the surface material, and then the reaction product floats away into space. The surface does not corrode the way iron rusts in water, where moisture and time and electrical processes work slowly from the outside in. Atomic oxygen erosion does not need moisture. It does not need time to set in. It happens on first contact, it continues on every subsequent contact, and every layer it removes is gone permanently. The mass of the structure goes up as exhaust. Most people who encounter this problem for the first time arrive at the same answer. If ordinary metals and polymers degrade in that environment, use something better. The logic is reasonable. Space exploration has always pushed materials science forward. Carbon nanotubes exist precisely because engineers and scientists needed something stronger than steel at a small fraction of the weight, and carbon nanotubes are stronger than steel at a small fraction of the weight. Graphene fibers, advanced carbon composites. These are not science fiction. They exist in laboratories. They have been tested. The specific proposal for a space elevator, the structure most commonly described when people discuss LEO megastructures, depends on carbon nanotube cables because the math only works if the cable is strong enough and light enough that its own weight does not exceed its tensile load before it reaches geostationary orbit. The problem is that carbon is not chemically neutral in the atomic oxygen environment. Carbon is one of the substances atomic oxygen attacks most efficiently. When an oxygen atom at 8 kilometers per second impact velocity reaches a carbon surface, it does not bounce off. It oxidizes the carbon on contact, and the product, a carbon oxide gas, releases into space. This is not a slow process. It is not a long-term concern for future generations of engineers. It is the same reaction that happens at the most structurally critical point on the structure continuously from the first orbit after deployment. To make this concrete, Kapton, which is the gold-colored plastic film wrapped around almost every spacecraft ever launched, used for thermal insulation, erodes in the LEO atomic oxygen environment at a measured rate of about 3 micrometers per year. 3 micrometers is roughly the width of a strand of spider silk. That sounds small. For a thin film on a satellite panel, engineers account for it in the mission design, schedule replacement, and move on. Now take that same reaction and apply it to a cable anchored at the equator and extending upward through the entire atomic oxygen density zone, through the most concentrated band of erosion from 200 to 700 kilometers altitude to reach geostationary orbit around 36,000 kilometers up. A cable that structure requires would be tens of thousands of kilometers long. Its most critical load-bearing segment, the section that carries the full tensile stress of everything above it, sits directly inside the zone where atomic oxygen flux is highest. Every year, the cross-section of that cable is getting thinner at the point where it can least afford to lose material. The year is not the problem. What the year means is this: the cable is not failing all at once. It is failing gradually, uniformly, invisibly, at the point where failure costs the most. The tensile strength of the cable is calculated for a specific cross-sectional area. As atomic oxygen removes material from that cross-section, the effective carrying capacity of the cable decreases. When the cross-section drops below the threshold needed to support the load of a climber vehicle in transit, the cable does not signal an alarm. It simply reaches the load it can no longer carry. A fracture in a cable at that altitude does not produce a controlled failure. Everything above the fracture point, potentially tens of thousands of kilometers of cable mass, no longer has a fixed anchor. It does not remain in orbit in a stable configuration. The orbital mechanics of a suddenly unanchored tether of that length and mass produce a debris event on a scale that has no historical equivalent. The altitude band affected would remain dangerous for human operations not for years, but for generations. That question has an answer. It's worse than the question. The answer most engineers reach is a coating. Not the cable itself made of a different material, but the cable's surface protected by a thin layer of something that resists atomic oxygen better than carbon does. Silicon oxide works, aluminum oxide works. Both materials sit on the surface and allow atomic oxygen to oxidize them instead of the structural material beneath. The surface erodes, but it erodes slowly, and the carbon underneath is shielded. For a satellite panel or a station module, this works reasonably well. Engineers calculate the erosion rate of the coating, determine how many years it takes to wear through to the substrate, and schedule replacement or design for a finite lifetime. The strategy is operational. It is used right now on structures in orbit. Trace what happens to that strategy at megastructure scale. The coating that protects the cable must be maintained continuously, because the moment it wears through to the carbon begins eroding. The maintenance interval is not decades. It is the time it takes for the coating layer to erode to substrate, which at the flux levels in the highest atomic oxygen zone is a matter of years at best. A maintenance program for a coating on a 100-meter station module is a scheduled activity. A maintenance program for a coating on tens of thousands of kilometers of cable requires the ability to reach and repair every exposed centimeter of that cable at a rate faster than the coating erodes. No vehicle, no robotic system, no inspection cadence makes that physically achievable for a structure of that length. The coating also adds mass. Not much mass per square meter, but a cable tens of thousands of kilometers long has an enormous surface area, and every kilogram added to the coating is a kilogram the cable's tensile load calculation has to absorb. The tensile to weight ratio is not a luxury specification in a space elevator. It is the fundamental constraint that determines whether the structure is geometrically possible at all. Add enough coating to survive the atomic oxygen environment, and the ratio shifts. The cable that was borderline possible becomes a cable whose own added protective mass pushes it below the threshold of geometric viability. There is a third option. Move the structure to a higher altitude, above the peak atomic oxygen density band, above 700 kilometers, where the flux drops and the erosion rate decreases. The problem is that the geometry of a space elevator depends on the anchor point being on Earth and the far end being geostationary, where orbital speed exactly matches Earth's rotation. The cable must pass through the atmosphere. It must cross the atomic oxygen density band. There is no altitude adjustment that moves the anchor cable away from the erosion zone and preserves the mechanical geometry that makes the elevator function. The erosion zone and the required cable path are not separately adjustable variables. They are the same volume of space. In 1984, a space shuttle mission retrieved a small tray of materials that had been mounted on the outside of a satellite called the Solar Maximum mission for just over a year. The samples had been placed there deliberately to test how different materials behaved in the actual LEO environment, not in a ground simulation. When the tray came back and the samples went to the laboratory, the results confirmed what theoretical models had predicted. Polymer and carbon-based samples showed measurable erosion consistent with the atomic oxygen flux models. The numbers matched. Not in a general way. Specifically, quantitatively, the erosion rates observed on recovered hardware agreed with what the physics of atomic oxygen impact chemistry said they should be. This was not a surprise to the researchers. The physics was already understood. What the measurement provided was verification. The environment behaves exactly as predicted, on real materials, in real conditions, and the rates are operationally significant. Not catastrophic over a year, not invisible either. The experiment closed the question of whether ground simulations capture the actual LEO environment accurately enough to trust for mission planning. They do. The models are correct. That confirmation matters for the same reason the coding strategy fails. When the models are correct, there is no hidden margin. Engineers in 1984 did not discover that atomic oxygen was less aggressive than expected. They confirmed it was exactly as aggressive as the physics said it should be. Every refinement in atomic oxygen flux measurement since then has continued to confirm the same erosion rates. The environment has not been found to have an off-season. It operates at the same flux rate day and night across every orbit for as long as the structure is at altitude. Every square centimeter of the International Space Station's exterior has been subject to this since the first module reached orbit. The station is roughly 100 meters across at its widest point. Engineers measure the surface degradation. They design replacement schedules. They accept that certain surfaces have finite operational lifetimes and plan accordingly. The station works within its design parameters as a structure intended to last decades, not centuries, with active maintenance by crews on regular replacement flights. A space elevator cable is 1,000 times longer than the station is wide. Its structural load is carried by its most eroded cross-section, not its average cross-section, which means the weakest point on the cable at any moment determines the maximum safe load for the entire structure. That weakest point is not randomly distributed. It is located in the atomic oxygen density band, at the same altitude every orbit, eroding at the same rate every orbit. You are not managing a structure with a maintenance schedule. You are managing a countdown whose duration is set by the erosion rate at the most stressed point on a cable you cannot reach for repairs. Surface engineering does not change what is true about the orbital environment. The environment is not a problem waiting for a clever enough material. It is a property of the space between 200 and 700 kilometers altitude, driven by solar ultraviolet radiation and Earth's upper atmospheric chemistry, neither of which responds to engineering requirements. Any structure placed in that band enters the same chemical environment that has been eroding spacecraft since Sketchlab. The physics does not have a deadline for improved materials. It runs on its own schedule. The proposals for orbital rings, tethered megastructures, and rotating habitats at low Earth orbit altitudes face the same constraint. The materials that make large structures mass-efficient enough to be worth building are the materials the environment attacks first and most thoroughly. The structures that could survive the environment long-term would require so much protective mass that the economics of building them collapse before the engineering does. Mars missions currently in planning will use transit vehicles spending months in low Earth orbit before departure burn. The transit vehicles will have surface coatings. The coatings will erode at the documented rate. Engineers will design for that. The question that remains unsettled is not whether a coating can protect a transit vehicle for 6 months. It is whether any architecture for permanent orbital infrastructure built to last not a mission but a civilization, can be designed around a material selection problem that the LEO environment does not permit to be solved from within the altitude where the infrastructure has to operate. The geometry requires the altitude requires the material requires the coating. The coating cannot survive the scale. Nobody has found the door out of that loop, because the loop is built from 4 physical constraints that do not negotiate with each other. What the first megastructure proposal that ignores this will look like, and what it will look like a decade after deployment, are 2 very different questions, and only one of them has a known answer.